Singapore.
This meeting is being recorded.
So for today's presentation, we'll be talking about QAOA as an algorithm, and also one of our software kind of open source software that we are working on called OpenQAOA, right? Yeah. So I think for most of you, the first thing that we want to, before we kind of move to the software, the first thing we want to ask ourselves is kind of, right, what is QAOA? So for this talk, we're going to talk about what is QAOA. We're going to go through an example with QAOA, the algorithm itself. And then we're going to talk a little bit more about what is OpenQAOA and how the open source software can help you in running your quantum optimization algorithms. Right. So I think most important question is, what is QAOA, right? Maybe some of you have been in quantum computing for a while and you kind of heard the algorithm by name, but not necessarily interacted directly or used the algorithm for any kind of purpose, right? So QAOA, its long form is really known as the quantum approximate optimization algorithm, right? And so this code actually comes from the original paper made by Farhi, right? It really is just a quantum algorithm that produces approximate solutions for combinatorial optimization problems, right? So in general, there are some really interesting features here. So one of the things is that why choose an approximate solution rather than the exact solution, right? So if we in general, there are many combinatorial optimization problems that are really interesting to study. But one of the issues with that is that they tend to be computationally hard, right? So we classify them as NP hard. So there are some of these NP hard problems, and in general, these NP hard problems, it's really exponentially hard for us to find the exact solutions to the problems, right? So because it's really hard for us to find them, usually what happens is that we prefer to have approximate solutions to these problems, right? So QAOA is one of the algorithms that allows you to get the approximate solutions. Also, approximate solutions are much faster to compute, which is why they are of interest to us, because the goal in industry is really to just get a solution. It's not imperative that we actually have a proper solution, the exact solution, I mean. Right, so how does the algorithm kind of look like? So the main overview of the algorithm, or what people like to talk about, is QAOA is a variational algorithm, and it consists of this quantum classical loop in your algorithm, right? So the diagram on the right is a very good example, representation of how this specific variational algorithm works, right? So we have a quantum circuit that's usually applied on the QPU itself. And this quantum circuit is parameterized by these two parameters, gamma and beta. And the idea here is that you use the QPU to compute the expectation value of the quantum circuit. And once you've obtained the expectation value, you would then feed that value of the expectation and the values of gamma and beta into a classical optimizer, right? And then this classical optimizer would then recommend a new set of gamma and betas, and basically it's like a loop. The new set of gamma and betas would then be run in the quantum circuit itself, and then you will get another set, a new expectation value. And basically the idea is that you have this loop until you minimize the expectation value, or until you reach a stopping criterion. So you would define some kind of way in which, let's say, like the expectation value has reached the lowest value, or kind of like maybe the expectation value stops improving, right? And then you would just cut off the circuit there. And once you've cut off the circuit with the stopping criterion, the values of gamma and beta are basically your optimized values, which is what you're looking for. And the idea here is that you can use this particular structure and particular algorithm to solve many quantum optimization problems, right? So as long as you can kind of phrase your problem in what we call a binary optimization formulation, you can kind of you can use this particular algorithm to solve it, right? So the part of this entire algorithm that interests us here, since obviously this is a quantum computing talk, the part that is really interesting for us is understanding a little bit more about the quantum circuit you can use for QAOA. So QAOA really, from a quantum circuit perspective, the structure really looks something like this. So at the start, you would have the all zero state. You apply what are known as header mark gates to each qubit, and then you apply alternating unitary operators. So you see this unitary C, and then basically what we call these two unitaries are coarse unitaries and mixer unitaries. So you apply them in alternating fashion, and you apply them p number of times, right? So if you ever hear somebody say, my QAOA algorithm has a p value of 1, right? That means you are actually applying the unitary one time, right? So you apply the coarse unitary once and the mixer unitary once. And if they say p times, you just apply the same thing, the same unitaries p times, right? And you can see that the unitaries themselves are also parameterized by gamma and beta. So in this example here, I've gone ahead and showed that like the values of gamma, beta are different, but then there are many different ways in which you can parameterize even how the gammas and betas themselves are parameterized as well, right? And so this algorithm, you can see it's really simple. It's really just alternating layers of unitaries, and then you have like a header mark at the start, right? Going further into kind of understanding what the unitaries look like, we have this example here. So focusing on, so what we've done here is we've taken like one block of the coarse unitary and one block of the mixing unitary and taken a closer look, right? So the unitaries can be further broken down into what 1 and 2 qubit interactions. And this is really important because one thing, the first thing is we define our problems in terms of these qubit, in terms of these 1 and 2 qubit interactions. And then the second thing is that these 2 qubit interactions will then be a lot easier to input into the quantum computers, because in general, quantum computers can perform natively up to 2 qubits, right? So you can see that the red block, which is the coarse unitary, is broken down into three different 2 qubit operations here. So this exponential is basically the same as the RZZ gate, right? So the RZZ gate once again can be broken down into even lower level native gates. Usually it's broken down into like C knots and some rotational Z gates, right? And so the coarse unitaries themselves, the coarse unitary is usually defined by the problem. So if when you've structured your binary optimization formulation in a certain way to solve a certain problem, you can then basically the problem itself tells you specifically how this unitary should be structured, right? And then basically you just apply the unitary. And then the second block, which is also known as the mixer unitary, in this case, there are many ways, many different kinds of mixers that you can use. The most common is just known as the rotation X mixer. The idea here is that once you've applied the coarse unitary, the mixers kind of allow you to explore a larger solution space, right? So the combination of these two and applying them in P layers will allow you to solve the quantum optimization. You will allow you to solve the optimization problem that you have, right? So so that's basically it when it comes to the QAOA as an algorithm itself. It's actually really simple. It's really just a quantum circuit with alternating unitaries. The unitaries themselves encode the problem, and then you would just run the circuit, and then you would use a classical optimization algorithm for you to minimize the expectation value. And when you minimize the expectation value, you again then get the solution to your optimization problem, right? So I think it's really straightforward how the algorithm works, right? So the next example. So now we kind of know what QAOA is roughly, right? It's a hybrid quantum classical algorithm that you can use to solve optimization problems. The next one is coming up with an example, right? So one of the more common examples, or one of the more easier examples to understand, is known as the number partitioning problem, right? So the idea of the problem is as such: given a set of numbers, the goal is to split the number into two sets of any size, right? And the idea is to minimize the difference of the sum of the numbers between the two sets, right? So I think this problem is really useful to visualize. So you can see a version of the problem on the right-hand side. You have a set of numbers here, and the idea is you want to split them into two sets of numbers such that the difference of the sum of the numbers is minimized. So in this case, you can see that the best solution here is this particular solution, where you have 4 on 1 and 113 in a second set, right? And maybe the more sharper of you might realize that, hey, there are multiple solutions, right? And that's true for this particular example, that you can have multiple solutions. So it's not necessary that like this is the only way the problem is formulated. So these multiple solutions are known as degenerate solutions, and in general, optimization problems sometimes will have more than a single optimal solution. So in this case, you can have 4 and 1 and 1 and 3, and that's also considered as an optimal solution as well. So these kinds of problems can be really interesting for us to study. Once again, why did we choose number partitioning as an example here? So something nice to understand is number partitioning is really simple to understand. So I think it's quite straightforward as a problem. Another thing is that it's a very well-studied optimization problem. So there are a lot of research papers, a lot of math textbooks talk about this problem itself. So I think it's really useful for us to use that. And one of the and also it's really easy for you to get hard instances. So if you just go online and you Google like hard instances for number partitioning, there are many problems that already have very good solutions, or already have the exact solutions, for example, where people kind of brute force the whole answer, and you can use those instances to test your algorithms, right? So I think it's because one of the things that we are trying to do here is also we want to make sure that we are writing algorithms that either are as good as the classical ones or can perform better, right? And so a good way to test QAOA is to kind of pick, you can kind of go around and search for all these hard instances for you to for your problem itself, right? So number partitioning, once again, a really useful problem, but maybe it's hard for us to kind of visualize how optimization problems can really be used in real life, right? It's maybe not so straightforward like in the case of number partitioning. So I've given a really kind of rudimentary example here. A very basic example is, let's say you want to use the same algorithm can be used for team balancing. So the same optimization problem can be phrased in a different way. So so in this case, you have what we call team balancing problem. So you start with a pool of players. Each player has a different rating score, right? And the idea is you want to split the teams into two balanced teams. So you have two teams of any size, where the players on both sides, when you sum up their scores, they are actually approximately equal, or very close to being equal to one another. And maybe because, and the reason maybe why you have that is because you want to have like players that maybe your game is more fair and balanced, right? Or maybe your game is a lot more interesting when the players have same skill level. So this is a potential way in which you can take an optimization problem and kind of turn it into a more real life example where you can then use to solve. And then you can use QAOA to solve problems like these, right? And these are not the only problems that QAOA can solve. So QAOA is a really robust algorithm because of a couple of reasons. But in general, QAOA can solve many different kind of optimization problems. So these are kind of these are the really interesting ones for many of us here. I think vertex cover, the traveling salesman problem, which is a very popular problem, your knapsack problem, the maximum cut problem, and the shortest path problem, right? So in general, if you can phrase any kind of real world application problem, and you can kind of phrase them in some of these optimization schemes, you can then just use QAOA to solve your optimization problem. And you're not really necessarily even limited to these 5 that we have here. So as long as you can phrase your optimization problems in terms of binary optimization, you can actually just use QBO to solve them, right? So I mean, you can just use QAOA to solve them. So so it becomes really useful that way, right? So before, I guess, kind of maybe before we move on to the next segment, where we talk a little bit more about OpenQAOA and how it can help you to solve your QAOA problems. Can help you to solve these optimization problems with QAOA. Is there any question?
Yes, actually, there's one question about this exponential operator. So Alex is asking if that's related to some Hamiltonian, that exponential operator.
Yeah. So right. So yes, the exponential that you see here, you have this HC, this Hn is really just the cost of mixer Hamiltonian. So yes, there is a relation to a particular Hamiltonian here. Yeah.
Okay, that was the only question.
Okay.
So if there's any question, any additional question? Oh, there's another one. Sergio is saying hi.
Okay, yeah, I can see. Yeah.
What is the difference? Okay.
Between the 2 types of blocks, right? Blue and red. Okay, so the red blocks in general are defined by your problem statement itself. So giving you an example is, let's say let's say you decide to choose to solve number partitioning, right? And what you have to do is you have to phrase your number partitioning problem in terms of what we call a QBO, unconstrained binary optimization formulation. So it's basically a formula. And the idea, and what you can then do with that formula is, once you phrase your problem in that formula, you can then convert it into this rate unitary here. So this rate unitary is defined by your problem statement itself, right? And then the blue unitary is just a mixer unitary. So what happens is that in general, the cost unitaries, right? For when you define your QBO problem, your cost unitaries usually use like ZZ operators, right? So if you know a little bit, when it comes to like quantum computations, if you just have ZZ unitaries without any kind of like basically without applying any other unitaries, you won't get any solution, right? So what you have to do is you have to kind of apply unitaries in different directions. So if you imagine your block sphere and you're just rotating around the same plane, you would probably just measure the same answer. And so the idea here is similar to that. It's just kind of when you apply the Rx or you apply these mixer operations, you kind of explore a larger solution space. And so that's the difference between the two. Is you can imagine the red one encodes the problem and the blue one tries to explore a larger solution space. So both unitaries have different use cases here. And in general, for the blue block itself, there's quite a lot of research done about what are the different possible kinds of mixer Hamiltonians or mixer unitaries you can use for any particular problem. So sometimes even the blue unitary, the blue block itself might not be restricted to your problem itself. So there's quite a lot of variations that you can do. And each of those different kinds of possible mixes can allow you to explore different solution space much more easily, right? So to give another very quick example here, when you apply this particular unitary that you see here, this rotation X searches the solution subspace, or you can think of it as a solution searches all of them rather equally, right? But then it's also possible for you to use, like, let's say, what we call XY interaction or 2-qubit interactions in the mixer Hamiltonian itself or the mixer unitary gates. And those 2-qubit interactions would actually allow you to search the subspace while maintaining like certain excited states if you are looking for interesting features like that. So yeah, so that's what these, so that's the basic difference between the red and the blue blocks.
Thank you. Since there are not any more questions, so I guess we can continue.
Right. Okay. Thank you for the question. So, what is OpenQAOA, right? So now we had a brief overview of QAOA, the algorithm itself. We have an overview of some of the examples that you can solve, some of the optimization problems that you can solve with QAOA. So the third part of this talk is really just what is OpenQAOA. So OpenQAOA is a library, a Python library for optimization with QAOA and its variations on quantum computers and simulators. So what it really is it's basically an open source package. And the idea of the open source package is because QAOA as an algorithm, while it's rather simple to define, it's a very complicated algorithm to implement, right? Because first, like if you remember the original structure, I told you there's this quantum hybrid loop, right? So you have your quantum circuit and you have your classical optimizer and you have to run them in a loop. And right now with many like the many quantum computing models, for example, like the one that I think IBM uses, right? So for IBM, you have to send the job back and forth, and this kind of back and forth, this model, which we call the cloud-based model, has a lot of issues as well. So for example, it's very common for you to send a job and then during the quantum optimization loop itself, where you require to send 100 jobs back and forth, there might be a break off in your QPU connection, and then you lose all of your information, right? So what you end up doing is you end up writing your QAOA circuit, you end up writing your optimizer, and then you end up having to write scripts that protect your code so that, like if there's any kind of, in case any kind of break happens with the connection with IBM Q, I'm able to salvage my code, right? And then on top of that, you want to try different types of circuit parameterizations. You want to do, let's say you want to try different kind of optimizers as well. You have to write your optimizers from scratch. So I think what OpenQAOA does is some of the problems that I've mentioned when it comes to actually doing QAOA on real world QPUs. The idea of OpenQAOA is we take all of that really difficult stuff, the really technical portions of it, and we help you implement all of that, right? So when you go and check out the library itself, you can see that many of the issues here have been defined for you, predefined for you, right? So we find a proper way to manage the QPU connection breaking. We help you write, so our code is robust enough where we can allow for different kinds of parameterizations for the values of gamma and beta I showed you guys earlier. We even have code that allows you to define your problem once and you can run it on different QPUs, different hardwares, different backends. Also becomes really useful for us, right? And then there are many different kinds of optimizers with integrated OpenQAOA with the optimizers from SciPy. So if you imagine the classical optimizers from SciPy, your SPSA, your vanilla gradient descent, your Kobila, your Bobby QA, and all of that, those are also available in OpenQAOA or will be made available over time. So the idea of OpenQA is really we resolve all of these problems when it comes to QAOA. So I guess the question that you're asking now is, okay, if let's say all of this is done for us, what do we do as users, right? So I think the key idea to take, the key point to take away here is that OpenQAOA allows you to focus on solving the problem at hand. It allows you to think more about the problem, which means think more about how you can phrase some kind of real world application in terms of an optimization problem, and then just using QAOA to solve it without having to think too much about how do I write my circuits, how do I connect with all the different QPUs, what do I have to do, and all of that, right? So it removes all of that and allows you to just automate your workflow. So using OpenQAOA to run QAOA algorithms is really simple, right? So I think this is a really nice slide that tells you. So the optimization problem, like number partitioning, which we talked about at the start, can be defined very quickly. So at the top here, you can see I defined the problem itself using NumPy. And then we have these helper problems, which which converts the set of numbers that you have into a QBRO formulation, right? So this QBRO formulation will then be accepted by what we call our OpenQAOA workflows optimizer for QAOA. And then you would feed your QBRO in, and then basically like in 3 lines, you can just get the answer. You just run q.optimize, and then we run the optimization problem for you. And then at the end, we do q.results.most probable states, which is just you can think of it as like the solution with the highest probability based at the end. And then you just get the solution, and OpenQAOA just gives you the solution, right? So you can see that all of the abstraction of like having to run how to have all of the circuits, how to kind of write the circuit, and all of that is gone. All you have to do is just understand how to use this QAOA workflow, and you can just solve any kind of optimization problem as long as you can formulate them in QBRO. So which is really useful for us, which is really useful because as part of the OpenQAOA package, we also have these problems classes that can help you to convert your problem into the QBRO formulation itself, right? OpenQAOA also has many other features other than just helping you run your QAOA algorithm. There are utility functions you can use as well. So in this case, if you look at the image on the top left, OpenQAOA has a brute force solution calculator, right? So if your problem is small enough, you can actually find the exact solution with the cost Hamiltonian, which is really useful for you to, like, let's say, cross-check your solutions. So in this case, we use the same problem, and you can see here that it found the perfect solution, right? So if this is the exact solution for the problem that you see in the slide before. OpenQAOA is also really useful because one of the things that you can do is you can just retrieve your previous results. So in the image on the bottom left, you can see there's this angles log, and the idea of the angles log is that it logs all of the history of the parameter that you are trying to optimize, right? And it's useful because obviously, like, you can kind of chart out the history. Maybe you are trying to see if there's any real change in the parameters gamma and beta. You can just plot all of that out, and it's really easy to retrieve those data because we kind of package all of these information for you. And lastly, and also one of the other things that OpenQAOA can do for you is we also have other helper functions that help you quickly visualize some of the key metrics that you want to look at. So in this case here, we have the cost value. So when you use an optimization problem, you're trying to minimize the expectation value. The expectation value also is what you're trying to minimize here. And so you can just plot the expectation value with just a single function here, right? So it's really simple and really easy to use. And one of the I think the more bigger features about OpenQAOA is that you can easily switch from different simulators. So OpenQAOA comes packaged with Qiskit simulators, PyQuil simulators, and also we have this vectorized simulator, which is a simulator that we internally created within Entropica Labs. And it's a really fast simulator. So if you guys are interested in looking at a really quick simulator, you can try the vectorized simulator here. And OpenQAOA works with all 5 of these simulators. And the goal of OpenQAOA is to expand to allow for more support for these local simulators as well, right? So one of the cool things of OpenQAOA as well is you can kind of transition between simulators and QPUs, right? So in this diagram here, you can see the image on the left, you are running one problem with the simulators, and the image on the right, you are running the same problem, but you're now using the IBM Q backend, right? So if some of you guys are familiar with how to use the IBM Q, how to use like Qiskit itself, you'll remember that you have to put in your API token, your hub, your group, your project, and you also just have to put the name of the backend itself, and in this case, it's just the QASM simulator. So just by writing these few lines here, you'll be ready to solve your particular problem on the remote devices that IBM Q has, right? So you can go from testing it on vectorized simulators to testing to running your actual problem on QPUs with just a couple of lines of code here, right? Yeah. So actually, the last portion of this talk is really just about talking about OpenQAOA. It's an open source software. It's on GitHub now, so you guys can go and check it out. There are many example notebooks that we've written for how to use the software itself. You guys should go and take a look at the software. One of the things that we are welcoming is, of course, if you guys are using the software itself, we recommend any kind of feedback that you want to give us. We also have a Discord channel where you can join. It's a little bit quiet right now, but we plan to have like more events, and we also plan to have these community calls where you can chip in ideas, and we can talk a little bit more about kind of the roadmap and anything interesting that happens within QAOA. And it's also a great place for us to kind of talk a little bit more about how we want to improve this package. Yeah, so really that's really just the more like communal aspects of the software itself. So if anybody is like loves to take part or participate in like open source software and wants to help us out, definitely check out these channels here, the OpenQAOA repository on GitHub and on the Discord channel itself. Yeah, so that's it for the talk. I can answer a couple more questions. Right, okay. Right, okay. So Hans is talking about he doesn't understand the zeros and ones. Okay. Right, okay. So yeah, maybe I skip a little bit on this solution. So if you remember the original number partitioning problem here, we have the numbers are partitioned into two groups, right? So you have group A and group B, right? And so when we want to formulate the problem, we formulate like group A as the number 0 and group B as the number 1. So when you measure your bit strings, or when you perform the measurements on the QPU, what the QPU returns is really these bit strings, which define which group the number enters, right? So in this case, you see 0 just corresponds with the first number in the set, 1 corresponds with the second. So in this solution here, you can see 8 and 7 are in the same group, and 2, 4, and 7 are in a different group. Yeah. So I think it's really interesting if you guys will pay attention to some of the solutions, right? You can see here that so when we use our default settings, you can see we obtain some solution with this energy here 4, right? But then when you use the brute force solution, we actually get the best solution. So you can see the brute force solution has an energy cost of 0. And you can see that like when we use the QPU, the solution is not very good, right? But then it's also because we are using an iteration of 5. But in this case, it's not really the QPU, it's just IBM's QASM simulator. But you can just change this to a QPU, and you can see that, and you can kind of compare how well the best solutions perform. Yeah. So do we have any other questions?
Yes, there's another one.
Yeah, okay.
Right?
Yeah, I can read it. Yeah. So this question, okay, yeah. So in OpenQAOA, we have, so your problems itself, you can also define your problem in terms of a Hamiltonian. So although not on this slide, OpenQAOA has a functionality where you can write your problem in terms of a Hamiltonian object, right? So you would normally you would define your problem with like what terms are you using, like your ZZ terms, your H terms, and basically like we have in OpenQAOA, you can check out, we do have a way in which you can define your problems in terms of Hamiltonian. And then all you have to do is just, once you've defined it in terms of a Hamiltonian, there's a way for you to convert it into QBO. And then once it's in the QBO format, you can just input it into OpenQAOA as well. So what I recommend you should do is, if you're not sure what I mean by that, you can check out the example notebooks. I believe we have a notebook example where you can see how we do that. Yeah. So the software itself has a way for you to convert your Hamiltonian into a QBO problem. And then basically, like, you don't have to think too much about like the Pauli gate orders and all of that, because once you have your problem Hamiltonian, once you convert it into your QBO problem, OpenQAOA takes care of how to run the circuits. And basically, like, it's not just running the circuit itself. So OpenQAOA, the main goal is to optimize the circuit as well, right? So in the future, we plan to add like qubit routing, for example, and we plan to add better decompositions. And the idea is, let's say you define the ZZ rotation, right? So in the example that I gave before, the Hamiltonian actually consists of what we call ZZ terms, right? And basically, like, you can define these ZZ terms will be converted into different kinds of 2-qubit operations. Yeah, I see a couple of people with raised hands.
Yes, but there's another one in the Q&A, so maybe we can answer that one, and we
okay,
the people's raised hand.
Right, will do, right? So William's question is, he's asking, can you explain the bit string energy? Okay, so I think it's easier for me to explain it with this, right? So for number partitioning in particular, you have this particular like pool of numbers, you split it into two different, and the goal is to minimize the difference, right? And so in general, when you're trying to minimize the difference, this difference is, you can imagine this difference is basically like your the energy level of the solution, right? So basically it's so the idea is the best solution would have an energy level that is very close to the ground state, right? And so when we say bit string energy, what we are referring to is actually this difference. So in particular for number partitioning, the lower the bit string energy, the more closer it is to the ground state solution. So that's what bit string energy means. Right. Okay, yeah, Hans, I think that's a very interesting question. So Hans is asking, for the number partition problem, is there a maximum size of the initial group that can be solved? All right, so this is a very big problem, right? For QAOA in general, because the number of, depending on the type of encoding that you are using, right? So for us, we are using a really basic encoding, right? So depending on the type of encoding you're using, you can solve many different sizes, right? So like in this particular case, where you have 4 numbers, you will require a QPU of 4 qubits in order to solve, right? So for example, let's say in this particular encoding, we call it like a 1-to-1 encoding, where 1 qubit is equal to 1 number. So if you have 80 qubit problem, you can solve 80 qubits. If you're trying to solve this with a simulator though, obviously it's proportional to the number of qubits in that simulator. So if you have like a 25 qubit simulator, it's going to take a while to run as well. Yeah. So there isn't really a size there isn't really a maximum size. You're not limited. The problem itself isn't limited to a size. It's you are limited more towards like whether your QPU can solve that problem for you. Like I think Andres brings up a very good question. Is what is the main advantage of this library compared to other known libraries? I think so. Within our company itself, we do a lot of research work when it comes to QAOA. So this is and one of the things that we found is that many of the libraries, when they talk about research or experimenting with QAOA, they can be they can lack some of the features that we ourselves want to use when it comes to research, right? So some of these libraries are also are missing like features that we want. Sometimes they are quite restrictive in terms of what you can and cannot do to your circuit, right? It's not very straightforward as to how you. So, for example, let's say if I want to do it on some other particular libraries, I would have to first understand some of the more the more complicated features on like their high level abstractions and all of that. And so, but the main idea of OpenQAOA is that it's an open source package that is like specifically developed for QAOA, and you can also run your QAOAs on different backends really easily. So our researchers have used it extensively, and there's quite a lot of like I mentioned earlier, there's quite a lot of benefit to be able to kind of like just run your problems very easily, very quickly, and all you have to do is just define the Q problem. So we believe the real advantage of this software is the automation that it creates, and then sort of like the other features that it has, which I didn't necessarily mention here, but if you take a look at the example notebooks, you can see that like there's quite a lot of buttons that you can push basically that allows you to modify. So for example, one of the features that you can do is, let's say you want to run a QAOA algorithm, but you want to append a circuit at the front while you're running, every time you run it. So we do have that feature built into OpenQAOA as well. Yeah. So that's quite, it's a very feature-rich software, and the whole point of the software is to optimize for QAOA algorithms. So everything on our roadmap when it comes to OpenQAOA is just QAOA focused. Is to make sure that we can get up to date with all of the latest research in QAOA, and also come out with the best, essentially like a solid package for you. Yeah.
Great. So I guess now we can start with people who raised the hand. So Mateo was the first one. So please go ahead.
Yeah, well, in fact, I put down my hand because somebody else asked my question. It had to do with the, again, with the advantage of use this OpenQAOA. For example, well, the answer, the question is already answered, but I was wondering because in Qiskit, you also have a QAOA implementation, and if you are working with Qiskit library, it's worth it to use OpenQAOA coupled to Qiskit, for example, in order to optimize the process and yeah, include this new library in your code.
Right. So it is true that there is a QAOA package in Qiskit. I think when like I was mentioning earlier, when we were originally designing OpenQAOA, there were quite a lot of features that we felt that the Qiskit library was lacking, right? So we wanted to kind of redesign a whole package whose main idea is to help to make it easier for researchers to use. So while you can use the Qiskit QAOA package, like I mentioned earlier, there's not as many. So for one, there's not as many optimizers that you can use, and then so OpenQAOA is, you can think of it as like it really is a platform in itself, because we've designed it in such a way where we can easily add many different kind of optimizers. So over time, we will be adding our own optimizers and our own research to it, right? On top of that, like QAOA is designed as OpenQAOA has like these block or smaller blocks of workflows like QAOA. And then if you check out the example notebooks, we actually have this thing called RQAOA, right? Which is the recursive QAOA, which is built on top of QAOA. And the only reason why we could do that was because we designed OpenQAOA in such a way where it was easy for people to build algorithms on top of that. But once again, it doesn't only run on Qiskit backend. So while it is possible for you to run on the IBM backend, OpenQAOA currently in development is also able to work with Bracket. So if you check out the dev branch, you can check out that you can use Bracket with OpenQAOA. You can also use PyQuil QCS if you have access to those, right? And the goal of OpenQAOA is to be an inclusive package that includes as many different backend providers. So that's our goal. It's not being restricted to just what Qiskit can do, but it's to try and open up ourselves to as many different providers as we can.
Okay, thank you so much. And again, thank you for the talk. It was very interesting.
Yeah, thank you.
Okay, so the second one was Patricia. She also lowered the hand, but you can ask for more details in case you still have the doubt. Okay, since she's not here, or the answer or the question was already answered. But yeah, okay, I don't see any additional questions, but I guess I think an interesting question for people would be if someone wants to know more about Entropica, like see the opportunities, like what should they do if they want to like focus at some point their career to some optimization problems? Because I see we have people here from different backgrounds, such as physics, engineering physics, electronic engineering, computer science. So it's like a wide range. So in general, what would be the suggestion to join maybe in the future and work for Entropica?
Yeah, no, I think that's a really interesting question. I think even for me, when I started in quantum computing, and I think many of you can relate, is I just finished my graduate school I just finished my bachelor's in university, and then when I left, one thing that I got into doing was like I got into machine learning, right? I think many of us probably got into that wave as well, and I used that to get a better understanding of very simple things like code design, optimization, how to use libraries, and all of that. And so I guess if you are really if people here are looking for like how can they be employed in quantum computing, especially now where the space is a little bit more different, right? You have softwares like Qiskit, you have many different softwares that you can use. I think particularly of interest for Entropica Labs is really just people who can use OpenQAOA or want to use OpenQAOA, right? So for us, if you know how to use the software and you are willing to contribute and you are always looking at interesting research ideas here and there, it will definitely be nice for us to work with you as well, right? So once again, a great way for you to work with us is to contribute to the open source package itself, right? I think that's a good avenue for everybody. And I think just like many other companies as well, whether it's Google or not, like, Google hires their employees based on how many, like if you've contributed enough to Keras, they will just hire you, that kind of thing, right? So I'm not saying, I'm not saying that like if you contribute to the software, you will get hired. But what I am saying is, I think if you are looking for a way, like a way to bring yourself into quantum computing, a really nice way is to choose like one thing and understand it really well. I think QAOA is really interesting, has a really interesting space in that, because at Entropica, we focus ourselves on QAOA, right? Like you can see we have an open source package. Like I just told you, we do quite a lot of research in OpenQAOA, right? In the coming months as well, we'll be releasing research on that topic. So if you're somebody who's like unsure where to kind of start off, I think it'll be really nice first of all for you to take a look at OpenQAOA as a software, and then maybe specialize yourself in the algorithm itself, right? And then one of the things that I believe we will be hosting in the future is we'll be hosting like hackathons where we'll be giving you like a problem statement and basically asking you to figure out how to maybe solve it, right? And QAOA will probably be one of the algorithms that you can use, right? So that's one. Another interesting one is, so I think for us, something that will be really interesting as well, that the community can, or you guys can maybe look at is optimize. There are many different kind of optimization problems that can be defined in this QBO format, right? The unconstrained binary optimization format, right? But the thing is that there really isn't a link, or it's difficult to establish a link between these optimization problems and real life problems, right? So it's sort of the same kind of link that you have with machine learning, right? But machine learning is slightly different because machine learning is about having lots of data and then trying to optimize that data. But optimization problems are really about having a problem where you're trying to optimize some particular function, right? And then optimizing that, right? So in many cases, like what interests us quite a lot when it comes to QAOA as well is if you can define some kind of real world application, right? And then phrase it in terms of an optimization problem and show that how, and maybe like use QAOA to solve it, or use any kind of variational algorithm to solve it. Like I think things like that are really interesting for us as well, because like I mentioned earlier, one thing that we've not seen so much of is kind of this real world to optimization problem linkage, right? And even if that, and when there is such a linkage, usually the problems are really challenging to solve and whatnot. So it would be nice if you are, let's say, if you are looking into this field of quantum computing and you want to try out optimization, maybe you have a background, right? So to add on really quickly is, maybe some of you guys are domain experts when it comes to finance, right? Or some of you guys are domain experts when it comes to, I don't know, like medicine, right? Right? You can probably come up with like, oh, like, you know, maybe this, like there's an optimization problem here where we're trying to find some genome, right? Can we phrase that in terms of a QBro problem? Right? Or stuff like that will really be really interesting for us as well. So like if you can come up with something like that, right? You know, drop a message on the Discord, talk to us more about like, you know, like what your problem is, like what's this interesting idea you have, right? And one of the things that, like I was saying, we're planning to do in the future is we're planning to have community calls, right? Community calls for QAOA. And when we have those calls, like definitely come up, stand on the stage there, give us your presentation, give us your best shot. And you know, like we definitely look forward to working with people who use our software as well. Yeah.
Great, thanks for the answer. And do you have additional social media apart from the Discord, so people can check when you host events or something?
I believe we do have, but like maybe you can check our website. Yeah, so one thing that you could you guys could do is you guys could check our website, which is entropicalabs.com. Yeah, I'll write it in the chat so you guys can take a look at it. And then I think at the bottom there there are links to some of our socials that you can get in touch with us, our emails and stuff like that. Yeah. But I think if you are looking to work on like OpenQAOA, definitely join the Discord and you know, and then drop your message there, and we can talk to each other. We can communicate through it.
Right. So people, please join the Discord. And there's an additional question in the Q&A.
Yeah, I think George has a question. Why does the library only take into consideration QBro problems? All right. I think this is a really interesting question. Give me a moment. Yeah. Alejandro, maybe. Let me see. Let me see if I have. Yeah. Yeah. Alejandro, if you don't mind, because I have a team member here who works a little bit more, who understands a little bit more.
What's the name?
Yeah, Vishal, I hope you don't mind. I'm gonna
Vishal.
name drop you.
Okay.
And yeah, Vishal, yeah. Vishal.
Mm-hmm.
Yeah.
The wrong
yeah,
one,
you can have him talk, yeah. Yeah, I think he will probably have an answer for that.
Okay.
Yeah, I can see he raised his hand, so.
Hi, can you hear me?
Yes.
Okay, perfect. Yeah, thanks, Shahidee, for the great talk. Yeah, I agree. It's an interesting question, but I think for now, the focus, like if I understood your question correctly, I'll try to give an answer. But I think with this package now, our plan is to try to focus more on the workflows that you're going to need if you want to run computations on quantum computing, for example. And at the same time, also focus a little bit on the algorithms, right? So there are two different aspects here. QAOA, of course, is the algorithmic aspect, and all the other systematic things and all the other things that you need are for example, like the stack things that you need to run computations on quantum computers, right? So there are two aspects to this library. And since most of the team's expertise now, given like what we've researched, the algorithms that we use for research in the past and so on, lie with QAOA, we decided to go and test this entire stack on this algorithm called QAOA. But having said that, actually OpenQAOA is designed in such a way that like the entire architecture, it's quite modular, right? So as Shahidee pointed out that in the future, you can add extra backends. So if, for example, tomorrow some XYZ company releases their own quantum hardware on the cloud, then you can quickly go and easily add it to OpenQAOA because of its modular nature. You can add extra optimizers in future as well. And on top of that, you also have the algorithm that's built, that's also built in a modular structure. So in a way, our plan in the future is to support like a family of variation algorithms. One of those algorithms is QAOA. So even though we're testing testing the waters with QAOA at the moment, but OpenQAOA, this open framework is not just limited to QAOA. It could be extended quite easily to other algorithms as well. Does that answer your question?
Sorry, I think that answered his question. Yeah, he said it.
Okay, thanks.
Thank you, Vishal. And now Hans also raised his hand, so please go ahead. The microphone seems to be open, but we can't hear you.
Yeah, sorry, I'm always having problems with unmuting my microphone. Thanks, Shahidee, for your talk. And I would like to ask you, please, to comment a little bit more about the approximated part of the title of the library. So it says it's an approximate method. It means the results are not so trustable at the end, or what is the level of approximation you work with this package? Thanks.
Right. I think if you look up the term like approximate online, right? Many people argue its definition, but the idea of the approximate when it's being in this particular context, right? is really referring to there is no necessary guarantee that you are going to get the exact solution or the best solution, right? But there is a way where you're going to get a good enough solution. And so, like, in a sense, this is what the approximate in QAOA stands for, right? I think if you are really interested in exactly how this algorithm works, like the paper and the reference, if for those of you that's a little bit more mathematically inclined, you guys can check that paper out, because in the paper they really explain how this algorithm come about, and basically the idea is the idea is rather interesting. It's just that, like, the solution, right. So if you let the algorithm run for infinite time, you will get the exact solution, or you will get a solution that is the ground state. But the question is, will you get in real life, will you ever get that solution? The answer is in real life, will you be able to get a solution? The answer is probably no, because you cannot run an algorithm for infinite time. So in that particular case, like, the solution here, because there's I'm not going to use the word like no theoretical guarantees, but in a sense, there is a reason why it's considered as approximate. Yeah.
So maybe, Shahidee, if you don't mind, maybe I can add a few lines to that as well. So I think it's an interesting question that you asked, and you focused on the word approximate, because for us, it's also like an important thing to like clarify, right? Because a lot of people, or like a lot of, let's say, media presence has made it believe that quantum computers can be used to like quickly find solutions to your problem. But if you look at the complexity class analyses for such problems, there is no guarantee that quantum computers can find solutions to NP-hard problems in polynomial time. They might not. It's unclear at this point, right? So, but QAOA is a different paradigm. So it's an algorithm that promises that you're going to find good enough solutions to your optimization problems, but you may or may not also find the ground state. Now, the fact that Shahidee said that if you let the algorithm run for infinite time, then you're going to find the exact solution, there's 100% guarantee of that, right? So that's like the asymptotic case analysis, that if you let the algorithm run for like infinite time, you will 100% get the exact solution of your problem. But as he also pointed out, that in practical situations, you probably cannot do that, right? You cannot let your algorithm run for like infinite time. And in this case, what infinite time basically means for QAOA is that you set the p-value like really large. So you remember the p-value from the circuit diagram, right? So you set the p-value really large. Basically, that's the asymptotic limit of QAOA of this algorithm. On the other hand, one important thing that I would like to point out is that most of these problems, like the binary optimization problems that we've considered in this talk, are these so-called like they actually also have these so-called approximate classical algorithms for them, right? Which means that, so even though QAOA is a quantum approximate algorithm, there are also classical approximate algorithms for such problems. And they guarantee, like they usually have some sort of guarantee that if your problem is of this type, of this subclass, and so on, then you have at least like some X percentage of guarantee that you're going to find the solution. So for example, just to take a concrete example, if you've heard of the problem max cut, then there's some D-regular graphs. Like if you want to solve max cut on some specific type of graphs, then you can get, for example, like 80% performance, at least as good as 80% performance from your approximate algorithms, right? So these are like really specific analyses that you can do on only like some problems that have some specific structures, right? So you can't, it's really hard to make generic statements. And that's one reason for that is because these performances vary depending on the problem you've considered, depending on the structure of that problem, and so on. And the same applies for QAOA as well. So QAOA is still, like, even though there have been lots and lots of research that's done on QAOA, it's still an ongoing research field, right? So there are some results that people have published that if you have like some 2 or 3 regular graphs and you're trying to solve max cut, then you're going to get at least some 70-75% approximation ratio, like which means like it's going to have like it's going in quality, it's going to be like 75% of your best solution possible, right? But these are asymptotic analysis only for specific problems. So if and I think, in my opinion, that these kind of analyses need to be done like on these specific case problems, and there is no like general statement that you can make that there will always be a guarantee of like some X percentage irrespective of the problem that you're trying to run. So sorry, I went on to blabber quite a lot, but I hope I partially answered your question.
Yeah, sure. Thank you. I appreciate you elaborate more on your answer. And I would like to take advantage to make one more question. Is have you had the chance to run your package, your algorithm, to solve a problem which can be solved through a classical algorithm, and then to compare the performance? And have you seen quantum supremacy somehow in this kind of situations?
So that's actually quite a difficult question, right? So I believe if I had seen quantum supremacy, then I would be quite rich by now. But so my answer to you would probably be no. But I think these questions are actually really difficult to answer in general, because the thing is that you might experience some, let's say, performance gain over classical algorithms for some problem that you've considered, right? But how do you go on to prove that this is not a fluke, or this is not just a chance of randomness, right? Because these algorithms, they're variational algorithms, right? So a lot of their performance depends on where did you initialize your parameters and how long did you run the optimization, and then which classical algorithm did you compare it to? Did you take into account the resource estimation that you're going to require from quantum computers and so on? And if you ran your results on a classical simulator, then did you take into account the fact that the real quantum computers will have noise in them? So how is that going to affect the performance and so on, right? So you get the point. There are lots and lots of caveats, and there are lots and lots of nuances that you can consider when you're trying to solve these problems. So in general, it's like a really hard statement to make that for this particular kind of problem, and if you try to solve it using QAOA, then you can have some sort of supremacy over classical algorithms. I think at the moment it's still undecided. So it's still in the gray area. So I wouldn't comment on that.
Hans. Seems you're still having problems with the microphone. We can hear you.
Yeah, finally it opens again. Yeah, I heard your answer. Thank you very much. No, I didn't comment anymore on that. I appreciate your answer, and I keep considering what I hear today.
Great, thank you.
Okay, is there any additional question just now to finish? Okay, since there are no more questions, so thank you so much, Shahidee. I really enjoyed your talk today, and well, it's actually the first time I met you, so it was very nice meeting you, and also you, Vishal. So I hope to see you again in the future events, or I don't know. But thank you so much for being here and talk to us about OpenQAOA and Entropica in general.
Yeah, thank you for having us, Alejandro. Yeah, it would be nice in the future, the future fall first and stuff like that, we come and give the talks. I think since we have like the open package now, whenever we can, we will try our best to join. Yeah.
Right. It's gonna be interesting to see this package in the future.
Yeah, looking forward to it. Yeah, and also like yeah.
Okay, so thank you everyone for attending today. So this is all for today. Muchas gracias a todos. Entonces nos vemos mañana.